How was yesterday, Kate?
Fairly boring, actually, which was good.
Yeah, that's good.
Yeah. Colorado was fairly tame. There were a couple of reports of some shenanigans throughout the state, but not bad.
So was that like a group that was it like with an organization that you were doing that, or were you kind of just going out on your own? And how is it all that violent?
Definitely not going out on my own. The organization is called Common Cause. It's a nonpartisan organization that is dedicated to making sure everybody can safely vote, regardless of who they're voting for. They had a team of legal professionals in a phone bank that took any reports of issues. So the volunteers, I think there are a couple hundred of us throughout the state, basically just showed up to polling places and made sure that there's adequate parking, signage, social distancing, all that kind of thing. And if there were any issues, reported those, and the phone bank of legal professionals then took the necessary steps.
That's really cool.
Yeah.
I just Googled Common Cause, check them out.
Good morning, everyone. I am going to jump right into it with a little diagram. So we're going to be doing a lot of diagramming today. I think the first thing is, can I get, so I'm going to show you this diagram. Have you all seen this before? I think Tim asked me for it and he said he was going to use it for his first How the Web Works class, but I wasn't actually there. So can I get like a show of hands if you have seen this diagram before? No, yes, some. Okay, cool. So I think that's okay if you haven't seen it before. So what I'm doing here is I've got a diagram of the postal system, of how the postal system works. And we can use this for an analogy of how the internet works, how the web works. So the internet is all about devices exchanging information. I send you a HTTP request, you send me an HTTP response. We have this client-server relationship. You can think of it just like two people exchanging letters. Well, one person needs something, or they want some information, or they want to send some information. They will write a letter, send it through the postal system, and it'll come back. Their person they write it to will write a response, and that will go back through the postal system and be delivered back to this person. So what I want everyone to do is I want you all to open up a notebook or like a new Atom tab or something, and go ahead and take 2 minutes to write down answers to these 3 questions. So take 2 minutes by yourself, and then I'm going to put you into some breakout rooms. Take about another 30 seconds to think through these questions. I was hoping to be able to share this diagram with you all, but it doesn't quite look like it's working. That's okay. I'm going to try to drop just the link to this diagram. Can someone click on it and let me know if you have access to it?
We don't. It says we need to authorize.
Is anyone able the link that I dropped in the channel, if you click on it, are you able to view this diagram? Did I drop that?
It says we don't have access.
Yeah. No access.
Can I not hear you all? Are you?
Hello? Hello?
Brian, can you hear any of us?
Brian?
Yes. Sorry. Hold on.
I can see the diagram.
Okay, I'm back. I can hear y'all now.
Yeah, it's the pizza example, right?
The pizza example?
Oh no, sorry. I posted that because Kate made it. And
Oh.
Not that one. Not that one.
All right. So just to be clear, I couldn't hear anything y'all were saying for the last 5 minutes. So did I miss anything important?
No, but we cannot open up the link. It
Okay.
says authorized.
I can
Okay.
access it for some reason.
Yeah, I had to go through all the authorization steps, but I can access it now.
Yeah, I had to like approve a bunch of stuff.
Oh,
Okay.
that's why. Okay. Well, sorry about that confusion. I'm off to a rough start this morning. I'm just going to drop these questions in your chat just so you have access to them. I didn't want to send you all off to the breakout rooms and not have access to the questions. So now I'm going to put you in breakout rooms. And yeah, go ahead and talk through in your room, talk through these questions.
Brian, are we going to a room?
Yeah, do you not have a room?
Not yet.
Oh, I see, Aiden. You don't have one. There you go. And do we have Kevin? Are you here? Do you see your room? Oh, there he goes. Tim, are you doing attendance?
Yeah, I already did it.
Oh, thank you. Thank you. I was gonna do that while they're in their rooms, but thank you. That's very helpful.
For sure. Today is the Ruby challenge, right? For the independent challenge, or is it something else?
Yeah, I was just gonna do the ones that we had done in the past for recreate, flatten, and what was it? String reverse and flatten.
Yeah, yeah.
I don't remember where those are actually stored. Hello, everyone. Welcome back. Let's go ahead and talk through some of these questions. So when you drop a letter in the mailbox, how does the postal system know where to deliver the letter?
Let's do random today. I guess you all can't see my screen. Trust me. I'm gonna get someone else. Kira, what did you all talk about for this first question?
We just mentioned that when you put your letter in the mailbox, postal system knows where to send it based on the address you write, which includes like the state and the zip.
Mm-hmm. Right. So we're gonna have this address. Kira, I'm gonna ask you first, and then maybe like, and you can bump if you're not sure. So when we're talking about delivering letters, we need to like have this address to know where to send this letter. In terms of like computers, when we're delivering HTTP requests and responses, how do we like address something on the web?
Are you referring to the IP address?
Mm-hmm. Yeah, that's exactly right. So I'm gonna go ahead and take some notes on this as well. It's a little bigger. So IP address is going to be an address that uniquely identifies a device on the internet. So this is analogous to our street address. If you want to send a letter, you have to address the envelope. You have to write down the physical address of where someone is located. Same thing when it comes to computers talking to each other. They need to know where they are physically located. So when I say it uniquely identifies a device on the internet, I would just be a little bit more explicit here. It like identifies where it is physically. So like, what are the like physical geographical steps that we have to take to get to this place? So we're very much thinking like, I think I have a diagram here just for talking purpose, very much think about like locations around the globe, things being stored in servers around the globe. Thank you, Kira. Let's go to, I want to hear some volunteers for this. How many street addresses do you have memorized? Let's open up the participants panel and let's do a little polling for this. Can I get a hand raise if you have one street address memorized? Oh, I just broke Zoom. Getting a million pop-ups saying like, this person raised their hand. Okay, go ahead and put your hand down or keep your hand up if you have 5 or more addresses memorized. Who has 5 or more street addresses memorized? Okay, looks like we've got 3 people left, 4 people. Let's go to 10. Who has 10 or more street addresses memorized? Is that Austin? Oh, everybody put their hand down. Austin, how many do you have memorized?
I think 5 exactly.
What about Carson?
I think 5 or 6.
And Brett, how about you?
Like, yeah, 5 or 6.
Nice. Yeah, so like at a certain point, our human brains are going to run into this problem of like, I can't just memorize every address, right? I can't just, that would just be an inefficient use of my brain space to just memorize things. So that kind of leads into the next question. Can I get a volunteer? When you want to mail a letter, but you don't know the address, let's go to Brett for this one. So as someone who has memorized all these addresses, if you don't have it memorized, what do you do?
These days, I typically use Google or just have them in my phone.
Right. So you've got your phone, you've got your Google, whatever it might be. You've got some way to look up the address, right? So that's a little small. So when we don't know the address I'll say by heart, if we don't have it memorized, we need to look it up, right? So I'm going to add on to this diagram here. Let me see if I can find a book. Yeah, perfect. Okay, boom. So I've got my diagram up here. My first step in here, I've got number 1. Let me zoom in a little bit. So number 1, you need to mail this letter. Then number 2, the postal system's going to deliver the letter. Number 3, your pen pal is going to receive that letter, whoever it is you're writing to. They're going to read it. They're then going to mail their response. The postal system delivers it back to your house, and then you read the response. So that's like the full front to back. I could also add in here, I'm going to add in a step 0. So I've got step 1 is to mail the letter, but how do we even know where we're mailing the letter to? Well, let's look up the address. That's going to be our very first step. So maybe I can, yeah, this is actually going to work pretty well. So rather than you just like mailing the letter, the first thing that you need to do is you need to get back an address from your address book. Oh, come on. Yeah, and then that's going to come back to you. There we go. So there's first this like lookup process where you need to find someone's address. Well, how does that happen when it comes to the internet? Well, that process is DNS. So I'm going to come down to this diagram here, and I first just want to write down what I said. So DNS, this stands for the domain name system. And DNS is all about looking up IP addresses. So if our IP addresses are similar to our street addresses in real life, DNS is similar to our phone book or our address book in our example up here. So in real life, in the postal system, I would need to look up an address in my address book. So a lot of times you'll hear that DNS is considered, I'll put this in quotes, the phone book of the internet. This is where we store these physical IP addresses. Now, in terms of in terms of like your physical address book, what I might do is I might look up someone's name. So I say I'm trying to mail Brett a letter. I'm going to look in my address book and I look up Brett Sherman and I see next to his name it says 1234 blah 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 wherever Brett's address is. In terms of the internet, in terms of looking up places by name, what is the name of the place we're trying to send our HTTP requests? What signifies the like the human readable name of a website? Can I get a volunteer? Kate.
It's the URL. Whether most people today don't know the whole URL, but usually the domain.
Right. So when you say URL, that means like the full thing in the address bar. And we talked a little bit about this in the beginning of the mod, but after you have this first slash, that everything after the first slash is the path. And note, that's not the slash that's part of the HTTPS part of it, but the first slash after that, that is the path, and everything before that is the domain. So as Kate pointed out, I'm on BE resources. Let me go to one that you're more familiar with, backend.turing.io. As Kate was saying, this address or this URL right here, the domain part is this part right here, backend.turing.io. So it's everything after the protocol, which is the HTTPS blah 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 blah, and everything before the path. So in this case, backend.turing.io. Another example of the domain would be like google.com. So back to my notes here, DNS, it's the phone book of the internet. More specifically, we're going to translate domain names to IP addresses. So another way of saying that is we're going from human readable to machine readable. So the domain name google.com backend.turing.io is the human readable name. That's how we as humans would identify it. But eventually we need to get down to 192.127.145, like all the raw numbers in the IP address that the computers can read, that they, yeah, I'll leave it there. Gary, you have a question.
Yeah, so my question was in regards to IP addresses and kind of how specific, right? So like with a regular address, like it literally, you know, I could go to a cul-de-sac with 10 houses that are all right next to each other. And like that street address for that one house will lead me directly to that one house. But like, for example, if I am at a company and we have, you know, 50 computers that are all tied to the exact same network in the same, geographical location, similar to having multiple houses on the same block, would the IP address be able to pinpoint one specific computer, or would it simply locate that group of computers in that location?
Yeah, so I'll be completely honest that this is not my like area of specialty, and I think that there's a lot of complexity that goes into that question that you're asking, Garrett. So I'll kind of like talk about what I know, but I just first want to be very clear, like I'm not the expert on this. So a lot of times when you have an IP address, depending on your like what it signifies, if it signifies a company, like if it is the IP address that signifies like the physical location of like specifically like a software company, some place that manages their own network. So not your house where you just like what most people do and what I do is like you just sign up with your internet provider and you say like I want internet, and they're cool, they take care of the IP address and all that for you, so you don't really need to worry about it. If you are at like a software company where the company is managing its network internally, what might happen is that the IP address might just signify that entire network, and then within the network there's a lot of handling that goes on within that network. So the IP addresses might look very similar up to the last number. So I've got an example here on the board. As you were talking, Garrett, I wrote this down. So for example, if we have an IP address that looks like this, this is what your IP addresses are going to look like. There's going to be 4 numbers separated by dots. So if I have 193.1.211.1.1, these first 3 numbers might signify the like entire like network, and then we might have in that a sub network where maybe 1 is the first computer to connect, then maybe 2 is the second computer, then there's like 35. So the final number might signify specific devices within that sub network. So that is all to say, like this gets very complicated depending on what's actually at the end of that IP address. A lot of times if you are using there are companies like Fastly out there, or Heroku is another example, where they are a platform as a service, meaning the IP addresses, the domain name system points to their internal system, and then from there they route it even further. So yeah, there's a lot of complexity that goes on with this. Joshua.
So would those additional routes within a network be like the ports of a server? How do I guess I'm a little unfamiliar with what a port actually is.
Possibly, yes. So what that would look like is rather than changing this 4th number, if I added in like colon 25 or something like this, now we're specifying ports, not just the IP address. And yeah, this could be a specific computer attached to this network. But again, this depends on like how that sub network is managed. I love that you all are curious about this stuff. This is very interesting. And like, I'm even trying to like figure it out in my brain as I'm talking through it. But I think the most important thing for now is just this concept of the IP address is going to identify some physical location in the world. So for instance, if I look back at my diagram here, I've got this little server. Maybe if I drop it right here, this would have a different IP address than if it was located maybe down here. So we're like physically identifying a place in the world. How do we get to this server? Let's go ahead and take a 5-minute palm, and we'll come back at 9:33.
Thank you, 33.
All right, let's jump back into it. So where we left off, our DNS, our domain name system, is how we look up addresses on the internet. So we're going to take our human readable domain name. We're going to try to translate it to a IP address so that we know where to send our HTTP requests. So coming back down to this diagram here, so this is a little bit more of like what the actual HTTP request response cycle looks like. So number one, the client is going to send an HTTP request. The internet is going to deliver that HTTP request to the specified IP address. The server reads the request. It creates an HTTP response. The internet delivers that back to your computer, and then your computer reads that response. Typically, that response is filled with HTML and CSS, and that's how your browser knows how to display a web page for you. So doing what I did before, I'll add in a, what do I want here? Let's find a server. So knowing that, just like what I did before where I added the address book into the other diagram, I'm going to add a step 0 here, which is going to be step 0, look up the IP address from the domain name. So your client, your browser is going to need to ask this DNS system. Oh, come on. Whatever, close enough. Your browser is going to need to ask this domain name system, the DNS server, to look up that IP address. So for now, we're just imagining this DNS server, just imagine it as one single server. So let me go back down to my diagram here. Let's imagine that this one right here is our like single DNS server. And let's say it's located here in West Africa. So what every computer in the world would need to do would say like, okay, well, if I need to go to google.com, I need to go ask our domain name system here in West Africa, I need to ask them what the IP address is for google.com. Or if I go to facebook.com, same thing, I need to go ask this specific server, how do I get to facebook.com? Give me the IP address. So for now, with this super simple version, every computer would need to ask this one. Let's put a label here. Let's say this is DNS right here. This one server is DNS. What is potentially an issue with this system? If we imagine that this DNS lookup, and by the way, something I haven't been explicit about, how does this like DNS system get this translation from domain name to IP address? Well, you have to register your website. That's why there's this whole like registration process. If you've ever tried to register a website before, you need to pay some money, and that goes towards getting you filed away in the domain name system to get a domain name IP address translation. I want to hear from the crowd. What are some potential problems from having this single DNS server? Curtis, what do you think?
The first two W's in www are World Wide Web. So if you have a single server, everyone is like going to be constantly trying to like hit that server. So there's going to be a lot of traffic. And also like, depending on how far away you are, it's going to take like shorter or longer to get that IP address.
Right. So a very important thing to keep in mind is that even though things on the internet seem to happen instantaneously, physical distance is still a factor. How far away computers are determines how fast we can send the electricity over the wires to get to where to send our messages where they need to go. So there are physical wires involved. So as a follow-up, Curtis, if I am located here in Central Africa, what's my response time going to be like from this DNS server?
I would imagine like 5 to 10 seconds, maybe.
Yeah, and you don't need to get an exact number, but compare that to what if I'm located now like over here in this eastern part of Russia? How do these two response times compare to this DNS server?
Oh, they'd be like much longer.
Mm-hmm. So the point is here, like if we just had this single DNS server, it would be, everything would take too long because everyone who wasn't located close to it, their responses would be a lot slower. So what we actually have, rather than this single DNS server, is we actually have a series of cascading steps that this DNS process needs to take. So let me move this DNS header. I'm gonna make this a little bit bigger. Let me move this out here, and let's dive a little bit deeper into what does this whole look up the IP address from the domain name look like. The first, and I'll actually put this down here. Yeah, that looks good. So the first server, so there's going to be a series of servers that are involved in this process. The first one that we're going to look up is the resolving server. So this server is typically managed by your internet service provider. That's not super important. This server is essentially, its job is to like manage this whole DNS process for us. So our computer only has to interact with this one server. We're gonna ask this server for the IP address and it's gonna send us back. And so that's why it's called the resolving server. It pretty much resolves this whole process for us. But what does this resolving server have to do to get the IP address? Well, that's a little bit more complicated. So let's first talk about this top level domain server. So there is another server called a this is actually not, sorry, I had the wrong one. This first one is actually the root server. So this server's job is essentially to, it's essentially to like kick off this whole process. I think there are 13 of these in the world. Let's see if I can do a quick Google on that. How many root servers are there? There are more than 750 users on all six. They are reachable using 13 numeric IP addresses, one per operating organization. Interesting. So it looks like there's only 13 IP addresses, but there's actually 750 of them located throughout the world. So this is essentially like our entry point for our resolving server. It's going to ask the closest root server to it, and that's going to be like configured by your internet service provider. It's going to know whichever one is the closest one to it, and that's going to be the first place that it asks. So we're going to go out here to this root server. And it's going to, the root server doesn't actually have any IP addresses. So what we're going to see throughout this process is that these servers oftentimes don't know exactly what the IP address is. What they do know is what server to send you off to next. So the next server that our DNS process, or that our root server is going to send us to, it's going to say, I don't know where this IP address is, but I know where the top level domain server is. So this one down here is going to be our top level domain server. What a top level domain is it's the dot whatever after your domain name. So for instance, for backend.turin.io, the top level domain is the .io, or it's the .com or .org. If I go to this website that I was just looking at, it looks like this is .se, which I don't know what that stands for, but there's all of these top level domains. So the next step in the process is all of those websites that have the same top level domain, they're going to be located on the same server. So then we're going to ask this TLD server what the IP address is. And again, this top level domain server is not going to know what the IP address is, but it is going to know the next server to send you to, which is called the authoritative name server. And the reason this is called the authoritative name server is because this one actually knows what the domain to IP address lookup should be. And how about like that? Sure. And that's pretty much our DNS process. So it's not super important that you understand this whole like root server, TLD server, authoritative name server process. That's not super important. What is important is that you understand that DNS is a multi-step process. And the reason that it's multi-step is because it has to do with geography. It has to do with, well, we want to send our requests through as little physical distance as possible. So the reason why we have all these lookups is so that we can send our resolving server, which is our like the one that's responsible for actually finding the IP address. With any one of these steps, we're only sending it so far to get the next step in the process. So even though it might seem like we're making this overly complicated, we actually make this a lot more efficient because we never go very far to get any one step in the process. And that is pretty much DNS. What questions do y'all have? Garrett?
Yeah, so like one thing I'm curious about is, so I play a lot of video games, for example, and oftentimes like there are some, these video games will have like one set of servers, so to speak, for like all of North America, one for like Europe, maybe one for like Australia. For example, they might have like their servers located in Chicago. So like I know from experience, like I might have like a ping of like 300 milliseconds if I'm in, or that's really high, but like 100 milliseconds if I'm in California going to Chicago. But then if I play like when I'm literally in Chicago, I might have like a 6 millisecond delay. And so I guess I'm curious, like for a game, like if I were to connect to a European server, I might get a 400 millisecond delay, which for a game can be devastating. But if I'm just going to a website, that's probably hardly noticeable. So I'm curious, like, how much is that? Are those types of servers different from this? Or like, because that 400 ping for like just a website doesn't seem bad. For a video game, it's devastating, but for just going to a website, it doesn't seem that bad.
Yeah, so I think the first thing is this concept of ping, like what does that really mean? So for instance, if we're trying to hit a server that's just like located somewhere in Europe, ping is essentially how long does it take me to, whoops, I didn't mean that arrow. How long does it take me if I just try to send a message that's just like hello server? How long does it take to send me back a message like got your message? So what Garrett is saying is if you're playing a game, like if you live in Europe and your game is hosted on that server in Europe, then you're going to have a lot better ping time, meaning you're a lot closer if you're located in Europe versus this person who's located in like Eastern Russia. So that's the first thing. The second thing, so Garrett, yes, you're right. If you are located physically closer to where your game is being hosted, most likely, yes, you're going to have a faster response time and therefore just like a more responsive gaming experience. To your second question about, not your second question, but to your actual question about like, how is that different than a website that's just like not really live? That comes down to that's not so much of like how, that doesn't have anything to do with like where they're located. So the servers are still located in the same place. It has to do with how they're interacting. And the short answer is that websites that are like used by users that are more of a like, I do something, I get a response, that aren't very like live like games are, they use a protocol underneath called TCP. And TCP is a protocol that is reliable and ensures reliable connection. Because as a user, like if I'm using Facebook or something, I want to be sure, like if I type out this post and I hit post, it's gonna post. Like I don't have to worry about like that message getting lost. So TCP is really reliable. What games use is not TCP because it's not as important for games that like every single input is received. What is important is that things are timely, as Garrett is pointing out. So underneath the hood, games use a protocol called UDP. And UDP is less reliable than TCP, but it's faster. So games will use UDP versus websites will use TCP. And if you're curious about that, I would just recommend looking that up. Like, what's the difference between TCP and UDP?
Yeah, thanks. I had no idea about any of that, so I appreciate it.
You're welcome. Yeah, so that's a lot of times we'll talk about like, let me look this up. What is this called? The OSI model. Perfect. So the OSI model, in computer science, we talk about abstractions all the time. You don't need to worry about something underlying that's more complicated if there's an abstraction built on top of it. This OSI model here is essentially layers of application for the internet. So when we develop our Ruby apps, our Rails apps, we're working at this top level application level. So notice how this is concerned with the end user, HTTP, DNS, all this kind of stuff. Programmers, web developers, we operate at the highest level of abstraction in terms of the internet, but you'll notice that there's all of these other layers underneath. Like physical. This is the like physical structure of wires going across the ocean and whatever. Then there's data link. This has to do with like switching, routing things. TCP is at this transport level. So this is you might hear people talking about packets, delivering packets across the internet. That's where this level comes in. So this is all to say, like, as developers, we don't need to worry about what goes on under the hood, but there is this rich world of like all these other things that happen without us even knowing about it. So if you're curious, this is another thing you can look up. Let's go to Will.
Yeah, sorry if you mentioned this, I don't remember, but who owns and maintains all these servers? Is it private or a mix of public and private?
Yeah. First of all, no need to be sorry. If a question's repeated, I'm happy to restate things if you need some clarification. There is a international body that governs these, and I think that I think countries manage these servers within their own country, but there is a like worldwide internet organization, and I'm blanking on the name right now, but there are like standards that are set by this organization. Does that answer your question, Will?
Yeah, I think so. I just wondered, like, if one of these servers goes down, does it fall to a government to make sure that they're maintained and operating, or is this like America is probably privatized or something? But just trying to understand the kind of like incentives behind maintaining these things. Whether it's...
Yeah, I think there's a whole chain of things. So like, governments are very complicated. I'm not going to pretend to know everything, but I think that it is some level of like, at the server level, there's a private company managing it. They are government contractors, so the government contracts out to these companies to management, and then the governments themselves of these countries are part of this international agreement of how this whole DNS system works. So it's up to the countries to manage their servers, but they can't just make up their own standards. Just like we have HTTP to make sure all of our clients and servers can understand each other, we need to have these agreed rules of DNS so that all servers, or sorry, all DNS lookups around the world happen the same way. So because the internet kind of transcends a specific government or country or anything, there needs to be this like international body that kind of make sure that everyone's on the same page. You can imagine how different the internet would be if there was like internet of the USA, internet of Europe, internet of Africa, internet of Russia. Like it would be much harder for us to talk to each other. George.
Yeah, as far as those like different servers and routers inside the DNS go, in your diagram, they kind of loop back to that home DNS. How do they know which order they are? Like you said that the root server doesn't know the IP, so then it sends it back. But like, how does that DNS know, like, where are we in this simple or whatever, this is probably simplified process, and how does that, if you could speak to that, that would be lovely.
Yeah, so this resolving server you can kind of think of it as like, its job is to manage this whole process. So when it comes to like, what do I do next? Where am I in this process? This resolving server is keeping track of it. So when you say it all loops back to this same resolving server. So that's kind of like the centralized place. That's the reason we have this resolving server in the first place. the resolving server has this root server just kind of like memorized. It says like, okay, I need to go to the root server to look this up. And then the root server will tell it where to go from there. So the root server will say, I don't know, but I do know where the TLD server is. And then the TLD server will say, I don't know, but I do know where the authoritative name server is. So it's kind of like it keeps track of this first step, and then every step of that tells you what the next step is. And this resolving server just manages that whole process. Another thing that I do want to say before we move on is I want to talk about caching. Let me put this up here, since this is like kind of a big topic and kind of like its own topic. So caching is storing the result of a complex operation for later retrieval. So if I ask you to do something really complicated, like I say, George, I want you to calculate how many taxes you're going to owe in 2021. Go ahead and just calculate that number. And I'm not an expert on this stuff, but I know that it's complicated, right? You would have to like look up the tax code without the help of like a actual accountant or anything. You would have to like look up the tax code. You would have to look up the tax bracket. You would have to like do a bunch of math. You would have to do all this stuff. Then if I asked you tomorrow, hey, George, how much taxes are you going to pay in 2021? You don't want to go through that whole process again to like calculate it again. You're just going to look at your piece of paper from yesterday and said, I already did this. I know what it is. There it is. I've got it right in front of me. So this is what caching is. Caching is a lot of times we don't want to do complex things multiple times. We'll do it once and then we'll store it. And if someone asks us for it again, we will just give them that answer. Now, one thing you need to be careful of with caching is cache invalidation, which is the question of how do we know when the data is stale? So for instance, George, if I ask you to calculate your taxes today of what you're going to owe in 2021, and then I ask you 8 months from now when you have a different job, well, you can't use the taxes that you calculated for me today because your income has changed. Things have changed, right? So this is where cache invalidation comes in. Yes, we do want to store these complex results, but we also have to know when they become stale, when they become invalid, when they're no longer relevant. So caching is like a big topic in computer science in general. There are multiple levels you can cache things. Your browser will cache things for you. Ruby will cache things for you. Rails will cache things for you. You can add in extra caching into Rails to be more specific about what you want cached for you. Your computer hardware will cache things for you. So you have registers in your computer called like your L1, L2, L3 caches, which determine like what things your computer needs to return if you are more into the hardware side of things. So that is to say, like, there's a lot of caching that happens in computer science. One level where things happen in terms of caching is this DNS process. So any results of this DNS process can be cached. So for example, if I am trying to hit a computer in China, if I go through this whole DNS process to find that IP address that I'm looking for, when I then need to, like, you don't just send one HTTP request to a website. I'm going to go, say it's an online shopping website. Well, I need to go visit that website in China, but then I need to add stuff to my cart. And then I need to edit my payment information. And then I need to check out. So there's this whole like multi-step process. Rather than going through the whole DNS lookup every single time, each of these, your resolving server will cache any of these steps on the process to make it happen. So I'll just put that as kind of like a parenthetical here. Any step in this process can be cached to make it faster. And you'll kind of see as I've like talked through all of this process, when it comes to like the lower levels of the internet, when we're not just thinking about the Rails and Ruby level, when we're thinking lower in terms of like, this is when you start to think about like Heroku. Where's my Heroku server stored? And how do we get the lookup for Heroku? Once you start thinking about the physical level, then you'll realize that like speed is super important. Speed, physical distance, all of these things that we don't normally have to think about come into play. And that is a layer of abstraction on top of our building our Ruby applications. Joshua. Joshua, do you have a question? Oh, he's frozen. Am I frozen? No, you all can, okay. What other questions do y'all have? That's everything I wanted to cover today. Do we also, I wanna look up the lesson plan too, because I think there might be some more resources in here if you're curious, deep diving a little further. How the Web Works DNS edition. Yeah, I will just drop this. It's not in the lesson plan, but I want to show you a video that I like for this. This one. And you'll see why I like it. It's very similar to like how I drew out these for you. So I think I'll leave it there. If you're curious about watching this video and maybe diving a little bit deeper, go ahead and pop that open. But otherwise, that's it for class today. So what we're going to do next is we are going to do a independent challenge. And this one is going to be, it's going to be a Ruby challenge. So we're trying to get you into the mindset of like, now that we're at the end of the mod, we're going to do some practice that's going to be relevant to everyone, no matter where you're at. It's going to be a Ruby challenge. So you can think about it like, if I'm in an interview, like, and I get this challenge, how might I approach it? So that's what we're going to do next. Let's first take a, you know what, I'll just go ahead and drop it for y'all. I think that'll be better. And then I'll close out this video and you all can take a palm. There's no submission, so don't worry about, actually, is Tim still on the call?
Yeah, I just jumped back on.
Thank you. Tim, would you mind dropping that challenge into the channel?